In this series of videos I'm attempting to repair this Hazeltine 2000 smart terminal. So far in this series I've dismantled the unit, taken all the boards out, and in the last video in this series I looked at the power supply, tested it, and since then I've had it running for several hours at about 50% full load. It didn't really get too warm. There's no fan on this at the moment. I've taken the monitor out and the fans attached to the monitor, but even so it didn't get particularly hot. So it looks fairly promising. All the supply rails seem to be within spec. They're slightly high, but that's mainly because they are not loaded up at the moment, so I will adjust those as we progress, and at the end, once all the boards are refitted, hopefully if it's running, we'll do a final readjustment of the supply voltages. I have reset this to 250 volts in this case by inserting the correct cards. It took me a while to find these, but they are part of the terminal that are screwed down to this bracket. So if you have one of these and you need to change the voltage, hopefully you'll have these as well. I don't know why certain things were unplugged. I haven't really found anything wrong with it other than on 115 volts I was getting a very high resistance on the mains cable, and that turned out to be one of the connections on the back of the selector sockets, and I remade the connection and it resolved that problem. So that may be what retired this unit in the first place. I've carried out a number of mechanical repairs. There was a lot of kind of dings and dents, and a lot of parts were bent. Quite a few fittings were missing, so I've replaced those. I've given the whole thing a really good clean inspection, and it does seem fairly good. It just needed a few very minor repairs. I didn't video them. These are just, as I say, things like straightening out brackets and that sort of thing. Electrically, so far it seems fine. I don't know the condition of the back plane. It's a combination of wire wrap and small push-on connectors. They are not gold-plated pins on these connectors, so I don't know what the condition of the wire wrap will be. We'll have to look at that as we go, but the rest of it seems fine. Huge transformer. The reason the transformer is so big, I touched on this in a previous video in the ADM3, and by fitting a bigger transformer you can kind of underrun it. You don't need to take the core quite as deep into saturation, so it produces less external magnetic field, and that's very desirable for a terminal when the transformer is so close to a CRT, otherwise it will cause distortion of the display. On that same subject, I do have an issue with this, or at least I will have an issue, in that this is a 60 Hz version of this terminal. And I explained this in the ADM3 repair, that in the ADM3 there's a dip switch. You can switch it between 50 Hz and 60 Hz. That's nothing to do with the data transfer rate, that's just the screen refresh rate. And the reason you might want to change it is because there are lots of magnetic fields floating around in any facility, and even within the terminal itself you still have a field coming from the transformer. You have ripple caused by ripple on the power supplies, and the result is you can get kind of undulations on the display when you're using a CRT. And if you synchronize those undulations with the mains frequency, then and the refresh rate of the display, then the undulations don't really show up. The display might be slightly distorted, but if it's static distortion then you don't really notice it. Whereas if it's constantly changing over time, you'll see it as kind of a wavering or a ripple effect, and it can be quite unpleasant to look at. So you can get around that by refreshing the screen at the same rate as the mains frequency. In this machine, unfortunately, it's a different circuit that's used, a different division ratio in one of the timers or counters, and so it means you have to you're supposed to swap the board out, but I don't have the 50 Hz board, so I'll try and have to figure out how to modify the board to run at 50 Hz. I'll come back to that later on if I can get the unit working. In the short term, we'll just have to put up with some ripple on the display if I can get it that far. I don't have a full schematic for this. What I have is a kind of a pseudo schematic, which is really just a series of block diagrams, and it's also a document for the A version. There were three major versions of the 2000. There was the A, B and C. The A was very similar to this. It had the rack with all the PCBs, but it had core memory. So it had some extra cards at the bottom that contained core memory, the drivers and the sense amplifiers. The B version, which is what this is, was very similar in terms of its logic circuits, but it has MOS memory, so single board MOS memory rather than the multi-board core memory. Also, the power supply was laid out slightly differently. And then there was a C version, which was very different. It had much bigger boards, and instead of having lots of little boards, they crammed everything onto just a low number of larger boards. And we've now got this thing up to the point where it's been running reliably. The power supply was behaving itself, left it running for quite a long time, didn't have any issues, so now we can start moving on to the boards. And as you can see, there are quite a few boards in this. There are two stacks of these, and the circuits are split across these. Unfortunately, while the functions are reasonably well divided across the boards, there is a lot of interdependency between the boards, so you can't just easily fit one board, test it and then move on to the next. You can do it to a certain extent, and that's how we're going to begin, but once you go beyond a certain point, you need to start looking at the machine in much bigger chunks using multiple boards. So I'll need to start plugging these back into the rack. In order that I can work on them, I need to be able to access them, and once they're fitted into the rack it will be very difficult. So I've made up a couple of risers, and I'll be able to use these in the rack to extend the cards out of the rack, and I'll be able to then access the cards if I need to. The only other complication with this is a lot of the boards, if we look at this one for example, it has slots for keyways, and they're all in different places on each card, and it prevents you putting the card into the wrong slot. In fact, it doesn't really, because some of the slots don't have keys in them at all, so you could in theory put it in the wrong slot, but all things being equal, it does help you to a certain extent to avoid making simple errors by offsetting it by one or two slots. But it means that in my risers I will have to cut matching slots, and because they're in different positions on different boards, as I progress I'll be cutting these slots as and when I need them, depending on which particular card I want to put into the riser. So question here of course is where to start. We've got the basic chassis, we've got the power supply, and as ever I'm going to start with the clock. So what I have are these are, as I said, pseudo schematics, and by pseudo schematics I mean they're really block diagram representations of the circuit rather than actual schematics, but they should still make life a lot easier. It's better to have these than nothing, and they do also indicate which particular card this part of the system is on. So in this case it's card A10, and this is where we'll be starting. It's the clock generator, and what we have here is a crystal controlled oscillator, divide by 2. We then have this what amounts to a ring counter. So the system works by generating 7 phased signals. So it's a bit like the ring counter in a microprocessor that is used to action certain events through an entire process cycle. And it generates 7 100 nanosecond pulses, and it just keeps repeating that, and they're fed throughout the system to make everything work. We also have this divider here which does something similar. It generates some system time pulses to drive certain parts of the system. And this is what we're going to start off by checking. The only other thing that we need, as you can see here, this line comes down here and it comes from the reset circuit, and that is on a separate card. That's on card A13. So what we need to do is get cards A13 and A10 fitted. Because it's only the reset line I'm interested in on A13, I'm not going to put it into a riser. I'm going to put that all the way into the rack, and then we'll check the reset line on the ring counter to make sure that that reset is doing what it's supposed to. If not, we'll come and look at the reset circuit, and then we'll start working our way through from the clock. We'll go through the divider and we'll see if this ring counter is working and also if this is working. So how do we go from this pseudo circuit to the actual PCBs themselves? And this is A10, and we can see that what we have is the crystal, and we can see it's connected through to this device. This is a 7400, and this is used as a simple oscillator. That then feeds up to this 7474, and I'm actually guessing here, I haven't tried this yet, but looking at the devices on here, this seems to make most sense. And I think this is the divide by 2 circuit that we have just after the oscillator. We then have the 7495s. We've got 2 of them, and these are 4-bit binary counters. So that would make sense to use these as the ring counter. We then have 7493s, again 2 of these, and these will most likely be used for the divider that we have down here. So all we need to do is dig out the data sheets for these devices, find out what the outputs are, and see if we're getting the expected signals. So what we should have is the clock, the divided by 2 clock, the reset circuit, the reset line coming in, and then we should see the phased signals being generated, and also the division signals. And that's what we're going to start by checking in this video. So I've printed off the relevant pages from the data sheets. So we have the 7495, that's our binary counter, and all we need to do is check the outputs to see if they are giving us the expected signals out. And we can do the same thing with the divide by 2, so that's the 7474, and we can see if that is giving us the expected signals. We can do the same thing with the 7493, check the outputs and see if all the expected signals are present. So I'll get this set up, I'll get the boards plugged in. I have done the usual static checks on the 2 boards we're going to be inserting. I've checked for shorts, made sure none of the caps across the supplies are shorted, and they seem fine at the moment. Now, having had a quick look at these cards, it seems that the 2 pins on the left on the A cards, that's the ones on the left as we look from the right hand side of the machine, are the power rails, and it's the same for the B cards, which are the ones on the right. This is the MOS memory card, except that these are fitted upside down. I think they did that to keep all the power rails running down the center of the rack. So as I say, I'll get these 2 cards, A10 and A13, fitted, and we'll start checking the signals and see if anything's working. I've got the 2 cards fitted. I've got A13 plugged in. That provides the reset pulse, or should provide the reset pulse. It can also be re-triggered from the keyboard. And I also have A10 plugged in, and that's the card that in theory should be providing this part of the system. So we'll start off in this top left hand corner. This device, I believe, I don't have the schematics, so I've just got this. This is as much information as I have, and I believe this device, this divide by 2, is this device in the corner. It's a 7474, and often they're used as divide by 2 counters, and it's closest to the oscillator as well. It doesn't always mean much, but in this case I had a quick look, and the tracks do seem to lead between the oscillator IC and the 7474. It goes up to this particular pin, and that's pin 3, and if we look at the spec sheet for the 7474, we'll see that pin 3 is the clock input, so again that makes sense. I haven't done a lot of in-depth reverse engineering of this. I'm just really going through and following it through as it seems to make most sense, but if you're not familiar with doing this, you might want to spend more time and try and figure out exactly how it's wired up. But I'm just going through this. It's very similar circuits that were used across multiple machines, so they are quite familiar even if you haven't seen the particular machine. We're hooked up with the scope. In another series I'm doing, I'm trying to point out different ways of testing and fault finding. Depending on what you're fault finding, different methods work better than others. In this case, for me, the best solution here is the scope. But if you don't have a scope, you could in theory get so far with something like this. This is just a logic probe, and I don't use this very much simply because I have a scope and other things, but if this is all you have, then they can still be quite useful. So we'll have a look at the signals with this as well, and you'll be able to see the advantage of using the scope. Okay, so we'll get this powered up. Now what we should see is it's a 20 megahertz oscillator, and what we should be looking at here is this is the clock of the second stage. So it's kind of uses two parts of the flip-flop. The first one is triggered directly from the clock, and then the second one is used as a kind of divide by 2, and we're looking at the divide by 2 input. So what we should be seeing here is a 10 megahertz signal. So we'll get this started up. It may do nothing at all, it may release the magic smoke. As I say, I've done static testing. I couldn't find any shorts on the board, but that doesn't mean that it's working. But we'll get it powered up and see what it does. The yellow trace is connected to the clock input of what should be the divide by 2. So we'll get this powered up, bring up the voltage. Okay, that's a good sign so far. We're getting something with just the time base on the scope, and it is indeed giving us a fairly good 10 megahertz clock. It's looking noisy because I don't have the ground probe attached to the scope probe as usual. So if the signal's not looking very good, what I can do is attach the probe ground lead and connect that, and then we can have a look to see how the signal actually appears. What we're seeing here is just kind of loop noise as well as the signal itself, but I'm just looking here to see if we're getting a signal at all. Not only are we getting the correct frequency, but we're getting quite a good amplitude frequency. We could of course use the logic probe here to see if this actually works, and we should see both the high and low LEDs come on when we look at the same point, because obviously it's going high and low. And as you can see, hopefully, they are both on. So that's looking good so far. That's proving that we are at least getting this part of the circuit working. The next thing we want to look at is the ring counter, and that's where things start getting a bit more interesting. So we need to get the next spec sheet. So looking at the spec sheet for the 7495, it's pins 13, 12, 11 and 10 that we're interested in, and we should be seeing the signals on those 4 pins. On each one of those we should have a 100 nanosecond pulse, and they should all be phased. So if you want to test them properly, you really would need to use at least 2 channels on the scope. And you can of course use the logic probe here to see if you're getting any activity, but it only tells you if they're toggling. It doesn't really tell you anything else. There are 2 of these devices on the board. Each one of these is a 4-bit device, but it's a 7-bit ring counter, so only the first 3 on the second device will be used. But we'll try probing these. So it's pins 10 through 13. So we'll try the logic probe first. And hopefully you can see that is toggling. We'll move on to the next one. Okay, so they're all doing what we would expect. What I'll do now is I'm just going to power it off, remove the clip, and we'll look at the same signals using the scope. We'll see how much more informative the scope can be and see if these are indeed 100 nanosecond pulses. Okay, power it back up. We'll check we're still getting our clock. Which we are. And now we'll see if we're getting the expected signals out of the ring counter. Try and keep my hands out of the way of the scope. So the scope is set to 100 nanoseconds per division. So that's the first. Okay, so we're definitely getting the 100 nanosecond pulses. I don't know if they're correctly phased. I'll check those off camera, but if they're there, almost certainly they'll be in the right phase. But all you do is just use 2 channels of the scope, of course. And the next thing we want to look at is whether the divider's working. So what we've done so far is check the clock's running, check the divide by 2 is working. We now check the ring counter, and these 7 signals that are used throughout the terminal seem to be working. And the next thing we want to do is look at this divider, which I believe is constructed from these 2 7493s. If we get the data sheet for the 7493, then what we can see here is we're looking for the QA, QB, C and D, and they are pins 12, 11, 9 and 8. So we'll check to see if they're doing anything. Just change the time based on the scope. These obviously slower signals because they're divided down quite a bit. Okay, so those signals seem to be present as well. Okay, so far it's looking promising. Everything on this A10 board, as far as I've tested, is working. We don't know if the outputs and control inputs are working, so there are some elements coming into this used to control the operation of this board. But so far it's working as it's supposed to. It's starting up. The correct timing sequence seems to be being generated. So we have the 7 signals that are used to drive the entire terminal are being correctly generated, and also the divider and decoder timer is working. So this board so far is behaving itself. The next thing we'll look at in the next video is the next circuits downstream, and we'll look at the horizontal drive generator. This is used to generate the signals for the display, as well as the counter and decoder that's used to generate the characters on the screen. So these are the next boards we'll look at in the next video.